We are members of the Robotics Science Club at Wroclaw University of Science and Technology. Since 2016, we have been focusing on underwater engineering by creating the PWr Diving Crew project and building ROVs and AUVs. We have been developing and improving the Blue Nemo underwater AUV drone project for over a year. Our cohesive team contains about 60 students. We actively participate in scientific conferences, competitions and events related to our field. The cylindrical pressure vessel is made of aluminum and the frame is made of polyoxymethylene. Both materials provide adequate strength while being resistant to water environment. The buoyancy is slightly positive, meaning that if energy is lost, the robot will spontaneously float to the surface. A balancing system is mounted inside lower tubes to keep the robot's center of gravity in place.
Blue Nemo is equipped with two processing units, NVIDIA Xavier and STM32, connected by CAN protocol. Microcontroller STM32 is responsible for steering the engines and effectors, but it also reads some data from sensors, for example, depth sensor BAR02. NVIDIA Xavier runs our Python code, responsible for object detection, signal processing and high-level task solving. It also runs the web graphical user interface for debugging the robot and verifying sensor readings.
After submerging, the robot will start to rotate around in search of a gate. So a coin flip is a piece of cake for us. We are planning to score extra points in this task.
In order to obtain the training data, we first collect recordings from the pool. Then we are labeling automatically as many images as possible, and the rest of the images are labeled by the team members using CVAT web app.
Apart from machine vision, the key to success are PID controllers connected to DVL and AHRS sensors, keeping the set speed and depth of the robot in changing water environment.
Our strategy to get to another task location is to establish the path using cameras and machine vision. It works by combining detections from our own implementation of OpenCV algorithm and a pre-trained neural network. This makes the algorithm more robust, especially if one of the methods turns out to be prone to on-site conditions. According to a previously made choice of a place, we are going to pump into a proper buoy recognized with a neural network object detection of an image.
Also, this is a good time to talk about our targets building process. Construction department managed to build competition targets using cardboard, PCV pipes and prints. Then we recorded all of the objects with an underwater camera to prepare datasets. Marker jobs construction gave us a challenge. First of all, we wanted to minimize the number of moving elements underwater, so we applied only one servo mechanism to drop both of the markers. We made additional ceilings to adjust it to work on larger depths.
Oh wait. But we have to take the cover out of the basket first.
Okay, calm down, I was just telling about this. At first, Blue Nemo was supposed to bump into the cover to drop it, but we were afraid that it was going to make the entire basket flip with everything inside it. So, we decided to apply a more sensitive solution, a grapple. It is a three-fingered construction that ensures traction and grip to get as many items as possible. Grapple's PCB allows to control the DC motor and read its position from the encoder. By that, we can estimate whether anything was grabbed or not and the grabbing strength. But how can we know if an item is in the grapple's range so it can start grabbing it? Well, there is a reflective distance sensor placed between grapple's fingers. This sensor is operated by STM32 microcontroller, and that data is then transferred to NVIDIA Xavier through CAN bus. To determine distance from the basket and the bottom of the pool, there is a sonar placed under the vehicle and a camera to recognize images placed inside the baskets.
To properly set up the vehicle before the shot, we use the front camera and machine vision setup on NVIDIA Xavier. As images have specific sizes, we can calculate the actual distance from them. It allows us to fire a torpedo in a close range, so it doesn't have to swim for too long and jeopardize the mission. There are two torpedoes built into Blue Nemo. Initially, they were supposed to be launched with the electromagnet and reed switch in the torpedo, but we decided that this solution is taking too much space. Therefore, we're going to start them with light. This type of launching offered the simplest and the most resistant construction. Triggering circuit of a torpedo is based on 555 timer, which causes launch torpedoes to work maximum 10 seconds after being shot.
There is one more thing that we almost forgot about. Hydrophones. We're planning to use 2 of them to navigate to both Cache or Smash and survive the shootout tasks. We're preparing a new PCB with microcontroller STM32 that will be responsible for data processing and returning the angle in relation to the place where pinger makes a sound. In order to do that, we have to train the neural network. There is a lot of work ahead of us, but we are sure we'll make it.
To move bottles from one table to another, we'll use the grapple that we mentioned before. The image from the main camera is going to lead us to an object. Then, by using another one placed in the grapple and a reflective distance sensor, Blue Nemo is going to grab the bottle and place it on another table. It may sound simple, but it's actually difficult to do that autonomically. Recognizing the proper table is going to be done with the camera placed under the vehicle.